Hello everyone. So this is our new series with respect to class 11th and related topics, and today we are starting with mathematics, which is called as language of physics, because when we start physics we need to have concepts of mathematics, right? Because without mathematics there is no physics. There are a lot of concepts of mathematics which you would be using in your physics in class 11, 12th and even ahead. So concepts like vectors, calculus, logarithm. So these are some important concepts which you should know before attempting physics, right? Okay. So today we are talking about the first topic of this series, which is vectors, right? Okay. So you would have known already that there are only seven fundamental quantities in physics, right? Which are the base quantities. Rest all quantities are derived from them, right? So if I talk about the fundamental quantities, let's say fundamental quantities. So what are they? First is mass, second is length, third is time, fourth is temperature, fifth is amount of substance, which means amount of matter or something. Sixth is what? Sixth is luminous intensity, and seventh is current, electric current, right? Okay. So these are the seven fundamental quantities, right? Any other quantity in physics can be derived from these seven quantities, right? Like you would have seen speed is a quantity, right? But speed can be derived by distance by time, right? So distance and time, length and time, these two are fundamental quantities. So any other fundamental quantity can be derived from these quantities. Let me give you one more example, right? You would have studied in your junior standards that force equal to mass into acceleration, right? Acceleration is nothing but velocity by time, right? And velocity is nothing but, what is velocity? Displacement by time, right? So again, if you see, we have mass, which is a fundamental quantity. We have length or distance, which is a fundamental quantity. We have time, which is a fundamental quantity. So there are only seven fundamental quantity. Rest all quantities can be derived from these seven fundamental quantities, right? Okay. So let me put the dimensions for these seven quantities, how they are represented, right? So mass is represented by m, right? The dimension of mass is called as m. Length is L, time is T, temperature is K for Kelvin, right? Amount of substance is mole, current is I, or and this is CD, right? Candela, right? So these are the way of representing these fundamental quantities, right? Okay. So let's take an example, right? Let's take an example. Uh, let's take an example. So this is formula. You can ignore the formula for now, but just to give you an insight of how everything can be derived from these fundamental quantities. So this is formula for viscous force, right? Like viscous force occur between layers of liquid. It's like a friction in between liquids, which is given by F force equal to coefficient into area into velocity by distance, which is called velocity gradient, right? So this coefficient of viscosity will be given by what? F by A into dv by dx, right? So now if I need to find the dimension of this eta, this is called eta, this symbol is called eta. So what is the dimension of this eta? So for that I need dimension of force, for that I need dimension of area, and for that I need dimension of dv by dx, right? Area is nothing but length squared. So you know the dimension of area will be L square. Simple. Okay. Force is what? Mass into acceleration, mass into velocity by time. Ignore the change in velocity as of now. Okay. And velocity was displacement by time squared. So the dimension of force will be m into distance is L and it is t square. So can I rearrange it and like mlt minus 2, right? This is the dimension for force, right? Okay. Now the third quantity is very simple. It is velocity. What is that? This is velocity by distance, right? So for dv by dx, so dv by dx is what? Velocity is again what? Dx by dt and into dx, right? So this is nothing but 1 by dt. Dt, you know, this is a small time, right? Which is equal to 1 by t and hence t inverse, right? So for all three expressions we have calculated, force is nothing but mlt minus 2, area is nothing but L square, and dv by dx is nothing but t inverse, right? Now can I put all this in this expression and find what will be the dimension for this eta, which is coefficient for viscosity, right? So eta will be nothing but force is what? mlt minus 2, area is L square, and this is t minus 1. So this is nothing but ml minus 1 t minus 1. This is eta, which is coefficient of viscosity. You can ignore what it is for now, but just to explain the concept of dimension, this is coefficient of viscosity. The dimension is ml minus 1 t minus 1. So I have represented this eta in terms of three fundamental quantities, right? Okay. Now all these quantities are classified in two different types, right? All these physical quantities are of two types. One is scalar quantity and another is vector quantity, right? So as you have come across these terms before in your junior standards as well, scalar quantity are those quantity which have only magnitude, right? Magnitude is nothing but a numerical value, right? So scalar quantity are those quantity which has only numerical values, right? So these are those quantities which has only magnitude or numerical values. For example, can we take mass, right? Mass, like we say that some body mass can be 5 kg, 7 kg, anything like that. So this is a scalar quantity. To represent mass, I just need one numerical value, which is magnitude, right? Then another type of quantity is what? Vector quantity. So what is a vector quantity? So a quantity which has both magnitude as well as direction is called vector quantity, right? So this has magnitude and direction as well, right? So let's take an example for vector quantity as well. Let's say force. So when we talk about force acting on any particular object, right? Let's say there is an object, right? And let's say there is a force acting here. So we are not just concerned about the magnitude of force, but we are also concerned about the direction of force, because direction will also determine my acceleration, right? So those quantity in which I am concerned about both magnitude as well as direction, those type of quantities are called vector quantities, right? Okay. What more difference can you talk when it comes to scalar and vector quantity? Okay. So for scalar quantity, we follow simple algebraic rules, right? Let's say we have some masses, right? 5 kg, 7 kg, 8 kg in a, let's say, a big box, right? And we need to find what is the net mass. So I can simply do it net mass equal to what? 5 plus 7 plus 8, which is equal to 20 kg. So this is a simple algebraic addition, and I can use all those algebraic additions and formulas for scalar quantities, right? But these formulas won't be directly used in vector quantities, right? Okay. Okay, let's understand these concepts by an example, right? So distance and displacement, you know these two physical quantity, distance and displacement, right? So what is distance? Distance is the net sum of total path traveled, right? Net sum of total path traveled by any object or a body, right? Displacement is what? Displacement is the shortest path between the initial and final. So it basically says how much objects had displaced from one point to another. It is not bothered about the path taken, right? So let's say there are 2 points, right? 2 points. Now this there is a particle at A which needs to move to B. It can go like this. It has reached B, right? So if I need to calculate distance, so I need to add this section, 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 this section, this section, and all those sections addition will give me what? Distance, right? Which is in meters. But if I talk about displacement, displacement is nothing but shortest distance. So you can just join this A and B, and this is the shortest distance between A and B, right? So now, can we imagine considering direction while calculating distance? No, right? So distance is a scalar quantity, right? It is the actual sum of all the path taken by this particular body. But displacement is a vector quantity. You see, displacement has a direction as well. So this is my magnitude of displacement, and this is my direction in which displacement I am calculating, right? But for distance, you just have magnitude. You don't have a direction, right? Okay. So let's understand by one more example. Okay. So let's say there is a big tube, right? Big tube, and there is a ball inside this tube, right? So this is a big tube. There is a ball inside this tube, right? Let's say ball has a velocity something like 3 meter per second in horizontal, right? But this tube itself has a velocity of 4 meter per second in horizontal, sorry, vertical, right? So this ball is moving with 3 meter per second horizontally, but this tube itself is moving with 4 meter per second, what, vertically, right? So let's say at I'm as of now, this is the time equal to 0 situation. The situation is like this. What happens at time equal to 1 second, right? So at t equal to 1 second, you see this tube will come somewhere over here, right? And ball will come somewhere over here, right? So horizontally, you can tell me that in 1 second, since it is 3, the distance this ball will travel is something like 3 meter, right? Distance it will travel is 3 meter. But this distance this pipe will travel is something like 4 meter, right? This tube has traveled 4 meter vertically, this ball has traveled 3 meter horizontally. So what is net displacement is of this ball, like how much it has shifted, right? So it is this, which is 3 square plus 4 square under root. This is a right angle triangle and this is a hypotenuse which is 5 meter. So net displacement of ball is what? It is 5 meters, right? So it's not that it is 3 plus 4 directly and 7. No, this quantity which I am calculating, which is displacement, it has a direction component as well, right? So ball has displaced 3 meter, the tube itself has displaced 4 meter, which in turn gives me the net displacement as 5 meter. So you can see the we are not applying normal algebraic rules here, right? So these rules which we just use in a triangle format, this is called as triangle law of vector addition, triangle law, which we'll discuss in coming time, right? Okay, this is clear. Okay, so let's talk about vector. Scalar is very simple to deal. We need not talk about scalar. We have already talked a lot about scalar in our junior classes, right? So let's talk about vector. Sorry, vector. So I already explained that all those physical quantities which has magnitude as well as direction are vector quantities, right? Okay, so how a vector is represented, right? So a vector is represented by an ray like this. You see this is kind of ray. So a vector is represented like this is a structure by which we can represent vector. So the length of this particular ray gives me the magnitude of vector, right? Magnitude of vector, right? Okay, and this arrow is pointing me the direction, right? Direction, right? So this arrow is the head part of vector, right? Head, and this is the tail part of vector, right? Okay. So shorthand representation of any vector, let's say this is a vector AB, so shorthand representation is AB, and then you have to put this vector symbol on the top of it. So this is AB vector, right? So if you write normal AB equal to 5 centimeter anything, this basically means this is a scalar length, it has value 5 centimeter. But if you are writing AB vector, you need to write magnitude as well as direction, right? Okay, clear? Okay. So next topic is unit vector. Unit vector. Before going to unit vector, let's say AB is a vector. AB vector, right? This is a AB vector. This has magnitude as well as direction. So magnitude of AB will be represented by mod of AB vector, right? So this is how we represent magnitude, right? Direction, let's not go into direction now, but we will talk about it soon. So unit vector, as the name suggests, a vector which has magnitude of 1 is called unit vector, right? But since it is a vector, it should have a direction as well, right? So to define unit vector, I can define it like that: a vector divided by its magnitude is called unit vector, right? Right. So let's say n is the vector, right? N is the vector, right? If I divide n by its magnitude, it gives me a unit vector of n, right? And if it is represented by n cap, a cap is placed on the top to represent the unit vector, right? So n cap is a unit vector which has same direction as n vector, but its magnitude is always 1. So you can write that magnitude of unit vector is equal to 1, right? The direction of unit vector is same as the original vector, right? Okay. So why unit vector is needed, right? Why a unit vector is needed? So by adding unit vector to any scalar quantity, we can create vector, right? So let's say there is a quantity AB equal to 5. So this is a scalar quantity of magnitude 5. It does not have a direction. But if I write AB vector equal to 5 n cap, this is still a quantity which has magnitude 5, but now it is a vector quantity and it has a direction which is specified by this unit vector, right? This unit vector has not changed magnitude of this particular quantity, but it has given a sense of direction to it, right? Okay. So let me talk about unit vector along axis, right? So axis looks like this. You have, let's say, you have x-axis, you have y-axis, and then you have z-axis, right? Okay. So vector can be represented along this axis as well, but to represent a vector you need a directional quantity. So we need to specify unit vector along all these three axes, by virtue of which we can represent any vector quantity, right? So unit vector along x-axis is given by I cap. Cap is the representation of unit vector. Unit vector along y-axis is represented by j cap, and unit vector along z-axis is represented by k cap, right? Simple. Okay. So let's say I am given a vector 3 I cap, right? I am given a vector 3 I cap. This has information, right? That this vector has magnitude 3 and it is in the direction of x, right? So this let's say this 3 0 is the point. So this is 3 I cap vector, right? This vector is 3 I cap vector, right? Okay. Now let's say the magnitude of vector is 3 I cap plus 4 j cap, right? 3 I cap plus 4 j cap. Now how vector will look like? 3 0 will come here, 0 4 will come somewhere around here. So vector will somewhere it will look like this. This is 3 I cap plus 4 j cap. It is lying in xy plane, right? And what is magnitude of this vector? You can see this is 3, this is 4. So magnitude is under root 3 square plus 4 square, which is 5, right? Okay, clear? An angle, obviously you can calculate. The tan theta is nothing but 4 by 3, and then you can calculate theta is what, right? So this is how we can calculate the magnitude and uh, angle for any vector as well, right? So if I generalize it, so if a vector is represented somewhere like ax I cap plus ay j cap, right? Let's say the vector is called as AB vector. It is ax I cap plus ay j cap. So what will be the magnitude of AB vector? It will be nothing but under root ax square plus ay square, right? What will be the direction of this? So direction with respect to axis will be, let's say theta is the angle it makes, so it will be tan inverse ay by ax, right? Clear? Even if I add az k cap here, this will just make it az square, right? Clear? So I am considered 3D now, right? Okay. So next topic is equality of two vectors. Equality of two vectors, right? Equality of two vectors, right? So equality of two vectors, right? So what is the condition on which two vectors will be equal? So two vectors are equal when their magnitudes are equal as well as their directions are same, right? So you can't just compare the magnitude and say that vectors are equal. Vector is has magnitude as well as direction. So two vectors are said to be equal when they have same magnitudes as well as they have same direction, right? So let's say this is a xy plane, right? So this is a vector in this xy plane. Let's say AB vector. This has magnitude of 5 and direction you can see, right? So if I need to make a vector equal to AB, I need to keep the same magnitude as well as same direction, right? So let's say this is CD vector, right? This has magnitude of 5 and this is parallel to AB. Now you can say that CD is the vector which has same magnitude as AB vector and it is in the same direction as AB vector. Hence these two are equal vectors, right? And this also says me that I can project AB vector to any point as long as I am parallel to it and I am keeping same magnitude, right? So this vector is also equal to AB vector. This vector is also equal to AB vector. So I can project n number of vectors to which is equal to AB vector, right? And that does not change anything to AB vector because it is still having same magnitude and same direction, right? Okay. So now addition of two vectors, which is a very important topic, which is addition of two vectors. Addition of two vectors, right? This is what is triangle law of vector addition. Right. Okay. So this addition of two vectors basically says if two vectors are arranged in this fashion that tail of another vector is lying on head of the first vector, right? If two vectors are arranged, let's say this is AB vector and this is BC vector. So if two vectors are arranged in such a way that tail of one vector is lying on head of another, so resultant head will coincide with the head of the another vector, right? So my AB is first vector, let's say, and my BC is another vector, right? So you see that the tail of CB or BC is lying on head of AB. So resultant will have its head coinciding with BC, right? Okay. As just now I explained that a vector can be projected anywhere parallelly, right? So let me try to project this vector, right? So if I try to project this BC parallelly to this AB, so it will look something like this, and this is still my resultant, right? So if I have two vectors like this, I have resultant like this, something like this. I'm not bothered about the value, the direction, everything. I'm just talking you how can we determine the resultant, right? So this is the simple way of telling the resultant, right? So let's say this is x-axis, this is y-axis. There is a vector 3i cap, there is a vector 4j cap. Resultant will be somewhere in this direction, right? Clear? And this is what comes from the triangle law, which I just explained on how a vector placement should be there. But this is how we can see it easily, right? Okay. Now let's talk about what is the magnitude, right? What is the magnitude of resultant vector? What is the direction of resultant vector? Right. Okay. So let's say we have AB vector, right? We have AB vector, right? And then we have, let's say, BC vector, right? So how resultant vector will look like? It will look like from A to C. This is the resultant vector. Please pardon my diagram. So this is the resultant vector, right? Okay. Now, can I project this BC to this point? Is that clear? Right? Can I project it here? Right? Now, I need to find what is magnitude of this resultant vector, right? What is the magnitude of this resultant vector? And what is the direction it is placed in, right? So to calculate direction and magnitude, let's say this is B, let's say this is D, and let's say angle between two vectors is theta, right? This is theta, right? And angle at which resultant is inclined to horizontal is alpha, right? Okay. So you might be thinking why I have placed theta here and not here, right? Because these two are parallel vectors, right? And I can place I can project a vector parallel to itself, right? Unless and until I'm maintaining the same magnitude. But only difference here is angle is only formed at a common point, right? At a common vertex. So to specify angle, I need to have two tails intersecting or two heads intersecting. Here it is like one tail and one head is intersecting. That's why I have indicated the angle at this point, right? So if you want to indicate an angle here as well, the angle will be like theta, right? Clear? And let's draw perpendicular from this point, right? Let's say this is CE. Clear? Okay. Now, what I need to find? AC, magnitude of AC and direction of AC, right? So magnitude of AB, what is given to us? I know the magnitude of AB vector, which is my first vector. I know the magnitude of BC vector, which is my second vector. I know the angle between AB and BC. Angle between AB and BC is, sorry, angle between AB vector and BC vector is what? Theta, right? What I need to find? I need to find the magnitude of AC vector, which is the resultant vector. I need to find the angle alpha, right? These two things I need to find, right? Okay. So this ACE is a right angle triangle. It's very clear that ACE is a right angle triangle, right? So in triangle ACE, right? Can I write it like this? The magnitude of AC square will be equal to magnitude of AE square plus magnitude of CE square. right? Clear? So AE, I don't know what is AE, but I know what is BE. Sorry, AB. Can I calculate what is BE and CE, right? Let's say how. So let me first write A is like AB vector plus BE vector square. So it's all magnitudes plus CE vector square magnitude, right? Clear? AB I know, but BE and CE is something which I don't know, right? So let me take cosine and sine relations and find it out. So sine theta is what? Sine theta is nothing but CE vector magnitude by BC vector magnitude, right? So CE vector is magnitude is nothing but BC magnitude into sine theta. Similarly, BE will be what? BC magnitude cos theta, right? Now let me assume this as equation 1, equation 2, equation 3. Let me place all these, right? Let me place all these together. So AC magnitude square will be what? AB, AB vectors mod plus BC vector cos theta square plus BC vector sin theta square, right? Now you can easily solve it. If you solve it, you will get AC vector square equal to, it is all magnitude. So AB vector square plus BC vector square plus 2 mod of AB BC cos theta, right? So AC vector will be nothing but under root of AB square plus BC square plus 2AB BC cos theta. So this is the magnitude of resultant vector, right? This is the magnitude of resultant vector according to triangle law, right? Okay. And also we need to find alpha, right? So what is alpha? Let me find it out like that. So tan alpha, if I find tan alpha is nothing but CE vector mod by AB vector mod plus V vector magnitude, right? So CE vector is nothing but BC vector sine theta, BC mod sine theta. AB is what? AB is already given to us, right? AB. And B is what? BC cos theta, right? So alpha is nothing but tan inverse BC sine theta by AB plus BC cos theta, right? This is expression of alpha, which is direction for this resultant vector, right? Okay. So let's say there are two vectors, A vector, B vector. A vector has magnitude A, B vector has magnitude B. So resultant vector, this is C vector, which has magnitude C, will be given by what? If the angle is theta, C will be given by under root A square plus B square plus 2AB cos theta, right? And if it is making alpha angle, so tan alpha will be given by what? It will be given by B sin alpha by A plus B cos alpha, right? Okay. So for any calculations now in physics, to deal with vectors, we'll be dealing with this particular expression, right? To find the addition of two vectors, right? Clear? Okay. So we just studied addition of two vectors, right? So if let's say C vector is A vector plus B vector, now how can we calculate the magnitude of C vector, right? So it's not like direct calculation which we had in scalar calculations, like we can directly algebraically add A, B and C and find C, right? So here what we did, we followed triangle law and then found the magnitude of C, which is nothing but it is given by under root A square magnitude A vector square plus V vector square plus 2A vector B vector cos theta, right? So this is the magnitude of C vector, right? So now this is added to the definition of vector quantity, and I can now define vector quantity are as those quantities which are having magnitude, direction, and which follows the triangle law of addition is called vector quantity, right? So remember, there are two types of quantity. First is scalar quantity. The quantities which have only magnitudes are called scalar quantity. Coming to vector quantity. So those quantities which have magnitudes, direction, and which follows triangle law of vector addition triangle of addition are called vector quantities, right? And why I'm adding this, because there are some quantities which has magnitudes, which have direction, but they are not vectors because they don't follow triangle law, right? Let's talk about electric current. So electric current flowing through any wire has a direction, right? So let's say there are two wires placed like this, and there is a junction here which is connecting these two. So let's say 3 ampere is current in this wire, 4 ampere is current in this wire. So current here will be what? 3 plus 4 equal to 7 ampere. It won't be 3 under root 3 square plus 4 square equal to 5. It won't be like that. So this has direction, this has magnitude, but this is not following the triangle law. So this is not a vector quantity. So these type of quantities are a separate group of quantities which we are not bothered about as of now. But yeah, this is how it is. Okay. So in next class we'll talk about some numericals on triangle law. We'll talk about different products. How can we multiply two vectors, right? Then we will start the original topics for class 11th, which is kinematics, rest and motion, right? Thanks.